Hello my people, I hope we're doing well today. This series of videos covers what are called Riemann sums, and we'll be evaluating them to begin with numerically. Riemann sum, now that we've done our sort of mechanics of anti-differentiation, we need to basically have a sort of conceptual road in, and that conceptual road in is through what are called area approximations. And it's sort of analogous to our entrance into the world of differentiation. So when we sought to enter the world of differential calculus, we used what is called the tangent line problem, right? And we used successive approximations of secant lines to gain an appreciation for the nature of the derivative. Now we are careful, and I've said this over and over again, not to equate the derivative with slope, right? So when I ask a calculus student what is the derivative, and they say the derivative is slope, I scream at them. But basically thinking about slope and how slope can become, how average slope or approximate slope can become instantaneous slope gives us sort of an entrance into the doorway, at which point we sort of need to jettison equating the derivative with slope, but merely recognize it as sort of the entrance into that sort of world, okay? Now, we began with two truths when we came to the tangent line problem. One is that any secant line connecting 2 points on a curve has a slope equal to the average slope of the curve over that specified interval. And the second one is the line tangent to the curve has the same slope as the curve at the point of tangency. Now, from these two truths, we use limits to transform our secant line, which we knew as our approximate slope, to a tangent line, which is the actual slope. And it looks something like this, okay? Now, what we're going to do here is let's just pick a point where we want to find the instantaneous slope, okay? And let's just take this point here, okay? And we'll designate it as x. What we know is that the actual slope going through that point, the tangent line, is going to look something like this. And I'm just sort of approximating it graphically, okay? The tangent line will look something like that. And we'll just label it as such, tangent line. But we're having a problem, right? We can't just find the tangent line at slope. We need to sort of back into it. So what we're going to do is we're going to take something similar. We're going to take a second point on that line, and we're going to graph a secant line. Okay? So hopefully this won't smear very much. Okay? And we'll call this the secant line. Now the secant line goes through the point f of x, and we'll call this over here not y or some other variable, but we'll call it x plus h, recognizing that we can just as easily designate that second variable for the distance between them. Okay? Now we know that the slope of the secant line which is our approximate slope, okay? So our approximate slope is, and we just use the slope formula, you know, y2 minus y1, x2 minus x1. And of course we can simplify that, as we've done in the past, to that. Now what we want to do is we want to basically shrink that h, right? Because the more and more we shrink the h, the more and more the secant line is going to be a closer and closer approximation of the tangent line. And I am going to take you to Desmos to check that out, okay? What I've done here in Desmos is I have designated the function y is equal to 1/4 x squared. And then I have created the tangent line, the secant line, based upon that. And that's just basically a simplified version of that secant line that secant line slope expression for this particular function. Okay, so that would be 1/4 x plus h squared minus 1/4 x, all of that over h simplified. That thing right there in this first parentheses. And then I put an h on a slider. Okay, now that right there is the tangent line. This right here is the secant line, and the difference between here and here is your h value. Okay, you happen to know it at this point. Your h is 3. But watch what happens as h gets smaller and smaller, right? When h gets down to 1, it's a much better approximation in terms of slope than it was over here at 3. This was, I mean, they're both positive, and they weren't too far off, I guess. But basically, once you get down to 1, they become a really good approximation, and then closer and closer and closer. And the moment that h hits 0, you get the secant line coinciding with the tangent line. Now that is analytically what we're trying to do when we talk about the slope of the tangent line. What we do analytically to show the same thing that we just showed graphically in that animation is we take the limit as h approaches 0 of f of x plus h minus f of x over h. And we know that, of course, as the limit definition of the derivative. Now that is how we entered into a discussion and into the world of the derivatives. And I wanted you to really focus on that because every time you took the derivative by the rules of differentiation, which we learned in chapter 3, I wanted you to remember that this is what was going on behind the scenes. Something similar is going to be going on for our world of integration, okay? Except for instead of secant lines to approximate our tangent line, we're going to be talking about area approximations. Now, like I said, as we seek to gain entry to the wonderful world of integral calculus, we find ourselves in this familiar circumstances. We can't just come right at it. Now, we will use the area under the curve and the geometric area formula to gain an appreciation for the nature of the integral, because when you say area under curve, that's a little more difficult. If we are asked to find the area under this linear function, well, that's easy, right? That's not a problem at all, because that doesn't require calculus. That requires geometry, right? Let's say I'm trying to find this area right here, the area underneath this linear between 2 and 5, right? Well, that area ought to be pretty easy to find, because it's either, if you look at it like that, it's a trapezoid, or you can think of it as the difference between two triangles, this big triangle minus the small triangle. But either way, it's going to amount to the same thing, okay? So if we think about it like this right here is your B1, this right here is your B2, and this is your height. Okay, well, that's basically translate that into what we know. This point right here, if I plug in 5 into here, I know that this is 5, 11. If I plug in 2 into here, I know that this point right here is the order pair 2, 5. So B1 is 5, B2 is 11. So the trapezoid is going to have a height of 3 and the bases of 5 and 11. So we know the area of the trapezoid is simply 5 plus 11, B1 plus B2, chopped in half, taking the average of them, right? Times the height, which is 3, that's 16 over 2 or 8 or 24. It's a little more complicated to do it by the difference of those two triangles, but it amounts to the same thing. You wind up getting 121 over 4 minus 25 over 4 being the areas of the big and small triangle respectively, and then the difference of those is 96 over 4, which again is 24, okay? So we don't need calculus for that, okay? But from the graph, we can see that the area we're asked to calculate, like I said, is a trapezoid. The problem arises, however, when we seek to find the area under a function that cannot be calculated with simple geometry. Right? Just like we did with the tangent line problem, we need to find a way to approximate the area. Specifically, we will be using rectangles, okay? So we're just going to be adding up in this video a bunch of rectangles, and we're going to be doing it numerically to drive home a particular point. We will get to sort of shortcutting that and using formulas when we get into future videos, but for right now I'm just going to beat this dead horse, and we're going to work through several, actually many examples in terms of figuring this stuff out numerically. Okay, so let's go ahead and let's move on to, and I first of all want to just think about it graphically. Okay, so let's take this function right here. Okay. This is obviously a cubic, okay, and we want to, let's say we're asked to find the area under the curve of f of x is equal to -1/5 x minus 7 and x squared minus 1. And I've left it in factored form because I wanted you to be able to see very clearly, right, why you have a 0 here at x is equal to 1, and why you also have a 0 here at x is equal to 7. Well, you know, x minus 1 and x minus 7 are both factors of the function, okay? So let's say I wanted to find the area between those, okay? Between not x equals equal to 1 and x equal to 7, but 2 and 6. So let's go ahead and just sort of draw vertical lines that designate our interval, okay? Now, let's go ahead and try this out using two rectangles, okay? Now, the question then arises, okay, well, how am I going to determine the height of the rectangles? And for now, we're just going to use the function value on the left-hand side of the interval. And this is actually referred to as a left-hand sum, but we'll get to that here shortly, okay? So what happens here is I basically am going to use this point on the left-hand side of this first interval to draw the function value and determine the height of this rectangle. And I'm going to use this point, which is the left-hand side of the second interval, to determine the height of this rectangle. Okay. And we have something that looks like that. Okay. Now we're not ready to calculate the sums. We'll do that here in just a moment. But I want you to see it, right? Now, how good of an approximation do you think that is? Well, the problem is that you have all of this area that is unaccounted for, right? And then you have all of this area which is unaccounted for, and only just a little bit of area sticking up over here that goes over, right? Which means that this is an underestimate. If you're trying to use it as an approximation, you should recognize the fact that if you were to calculate it and get an actual number, this is going to be an underestimate, okay? Well, let's go ahead and let's do more, okay? So instead of basically taking h, which was, you know, the distance between x and x plus h, down to 0, so instead of taking a quantity down to 0, you're going to be making a quantity larger, and ultimately we're going to be taking it off to infinity, but let's not get ahead of ourselves. We're going to do the same thing with 4. Okay? So we're going to subdivide this interval into 4 subintervals. All right, and again, we're going to determine the height of each of these subintervals based upon the function value on the left-hand side. That's an arbitrary choice, but I want to be able to compare one to the next, so I'm not going to change it. So we have this, and have this. Now, if you look at the previous one, right, we have sort of x is equal to 2 to x is equal to 4. This right here in the previous one was 1 subinterval, not 2. And so this new estimate actually gets rid of some of that green area from the previous one and sort of chops a little bit of it out, right? And because this is the difference between the one from the previous, having only 2 rectangles, right, and now having 4. So what we're going to do is continue to shade it in. And then let's talk about the interval from 4 to 6. That used to be one subinterval and now is two subintervals, right? Well, now none of it goes over, right? You have under, right? But you notice that what used to be here, what used to be an overestimate area is now under. Now, does that wind up nullifying the fact that it makes this a better approximation? No, because this sort of gain is worth more than this little loss, right? But it's almost a wash. But then let's go ahead and let's try and do it with 8 subintervals. And that's where we're really going to see the payoff in terms of actually, and I messed that up, didn't I? Yeah, basically, it actually needs to be up here, so it's more. So, sorry about that. But the point still remains. So let's move on to the next one, and let's do from 2 to 6 for 8 subintervals. Yeah, so my little mess up there is illustrative of the point that it's really easy to get jumbled up if you're not being careful and mistake left hand for right hand and everything like that. So you have to be, it's one of those things where you just have to be very, very particular and very, very careful as you're sort of, winding through these things. So that point. And if 8, I'm not going to have a line to guide me, so some of these in between are going to be ish, okay? So every time I go up, I'm going to draw to the left, and I think that'll keep me from making the same mistake this time. Go up and to the left. Let's go up and to the left. Let's go and as I'm drawing these, you're thinking to yourself, gosh, this is a lot of work. Yeah, well, doing the derivatives by limit definition was a lot of work too. But conceptually very, very important. And the same is true here, okay? Now, as I'm filling these in, you should notice that even more of that green area, which constituted the difference between the approximate area and the actual area, that green area between my rectangles and the graph are now becoming much, much smaller. There's going to be a whole lot less green, a whole lot less in the difference with this approximation. You just have this little bit right here, this little bit right here, this little bit right here. And so we can see as we sort of go from 2 to 4 to 8 subdivisions that what we really do get is we really get a much better approximation. And of course you're going to get a better approximation with 16 and 32 and all that sort of fun stuff. We're not there yet because all we've done here is basically talk about it graphically. In the next video we will begin talking about these numerically and actually computing, evaluating, calculating the approximate areas for any given number of subintervals given a particular function. So, bye.